All right, so this is still in chapter 5. We started the mean value theorem the other day. We're continuing. These are actually ideas that are extensions of the mean value theorem. Okay, so one of those ideas is this, that functions with the same derivative differ by, at most, a constant.
Oh, yeah, because constants don't get into the derivative.
Right, if you take a function add on 7 and take its derivative, what's the same as the original function's derivative? And that's the most they can differ by. They can't differ by anything other than a constant if two functions have the same derivative. So if f prime of x equals g prime of x at each point of an interval I, then there is a constant c such that f of x plus g of x plus c, f of x is equal to g of x plus c for all x in that interval. That's the math way of saying the sentence that I said at first. Okay, so let's find the function f of x whose derivative is cosine of x and whose graph passes through the point 0, 3. So what we're saying here is that f prime of x is equal to cosine of x. So what is the simplest function that has a derivative of positive cosine? Right? So that would be the simplest one. But it could have a constant associated with it as well that we don't know about. So we'll say that it's sine of x plus c. And then what we will do is we will use this, which is called an initial value, to solve for c. So if it passes through the point 0, 3, we know that 3 is equal to sine of 0 plus c. Sine of 0 is 0. So that means 3 is equal to c. So f of x is sine of x plus 3.
Are we going to get into the unit where we have to figure out the normal function, like the regular function from the derivative, super fast? Like
We're moving that way slowly.
I'm scared. If you could stop moving.
Inertia does not allow us to stop moving.
Irfan's not convinced we're just going to take a nice escalator ride down.
I'm going to apply opposites in greater force. Boom.
Good luck with that. I am the unstoppable force.
You're the only God.
Just create friction, Irfan.
And you are not the immovable object. That's the old, what happens when, actually the old version of it is what happens when an irresistible force meets an immovable object.
What would happen?
The musical answer to that is, and I don't know the song, something's got to give. It's a song about a guy who thinks of himself as the irresistible force and a girl who thinks of herself as the immovable object.
Why can't it be the other way around?
I suppose it could be, but
yeah.
Anyway. So this leads us to the idea of an antiderivative. So a function, notice this is capital F of x, is an antiderivative of f of x if capital F prime of x is equal to f of x for all x in the domain of f. The process of finding an antiderivative is called antidifferentiation.
They love using the word anti.
Prefix anti.
Yeah, anti's not a word.
Prefix is prefix.
And this is a great one for, if you're playing Scrabble. If someone puts different up there, you could add, you could add ation and have differentiation, and then you could come back and add anti to the front of it, and you could have a huge word.
You can get that triple.
If you got the space and the keys.
All right, so here's an example. Find all possible functions with derivative f prime of x is equal to 1 over 2x to the 2/3 power, period. So that's the first part. Then find the function that also contains the point 8, -5. So we're going to use that 8, -5 as an initial value after we find the general function. So probably want to rewrite this as f prime of x is equal to 1/2 of x to what power?
X to the -2/3.
X to the -2/3, exactly right. So we're beginning to do a little bit. We're not going to do a ton of this right now. We'll do more as we go, of thinking backwards. What could I have taken the derivative of that would have given me 1/2 x to the -2/3 power? For the time being, don't worry about the 1/2. Just think about what did the power have to be before I took the derivative.
1/3.
It's got to be 1/3. And notice that if I take the derivative of this, I'm going to get the x to the -2/3, but I'm going to multiply whatever's out here by 1/3, right? So I don't have a 1/3 here, do I?
No, but you can put something there.
So what I'm going to do is put a 3 and a 1/2 as factors, so that when I take the derivative of this, the 3 and the 1/3 will divide out to be 1, and I'll get the 1/2. And notice that it could be plus a constant. So when they say all possible functions, that's that plus some constant. So f of x is equal to 3/2 x to the 1/3 plus c. So you kind of see the thinking behind working backwards. So then what's called the particular solution, this, by the way, sorry, I should have said that first, is called the general solution. It is all of the functions who have this derivative, particular to this initial condition. We're going to go, okay, -5 is equal to 3/2 of 8 to the 1/3 plus c, which indeed is 2, times the 3/2 is 3. So -5 is equal to 3 plus c. Subtracting the 3, we get -8 is equal to c. So that our particular solution is f of x is equal to 3/2 x to the 1/3 minus 8.
Good stuff.
It's not so bad. Now, we will get to ones that are uglier, but not yet.
Not until the next page.
So, increasing and decreasing functions. This is actually not a calculus thing at all.
Is this algebra?
Right. But we use it in calculus. Okay? So, this is one where actually I had a long argument with somebody at the AP reading once where she was trying to apply, she said, no, that's a calculus definition. I'm like, no, it's not. She was wrong. I was right. Yes?
What's the specific difference between calculus and algebra? It kind of feels the same to me.
Well, so if you're taking derivatives or antiderivatives, it's calculus. If you're not, it's not.
Is that all calculus is concerned with?
Derivatives, antiderivatives, and then if you get a little further, then we will get also sequences and series. You can do infinite series with them as well, but we won't do that. So let f be a function defined on the closed interval from a to b. Okay? So it exists everywhere. Notice we didn't say that it was continuous or differentiable. Okay? And let x sub 1 and x sub 2 be any 2 points within that interval. So f increases on the closed interval from a to b if x sub 1 less than x sub 2 lets you know that f at x sub 1 is less than f of x sub 2. Okay? And f decreases on the closed interval from a to b if f if x sub 1 is less than x sub 2 implies that f of x sub 1 was bigger than f of x sub 2 for all points within that interval. Okay? That's the definition of increasing or decreasing. And what happens is that we're going to apply something calculus to it in a little while that makes some people
shiver.
Well, it makes some people, they try to make the calculus be the definition, and it's not.
That's what the woman did.
Yes, she did.
Where was she from?
I don't know.
Probably some flyover state. Ohio.
So, this leads us to a corollary of the mean value theorem. Remember, a corollary is something that is true as a direct result of something else. So, if f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, all right, that means the mean value theorem applies, so does the intermediate value theorem. If f prime is greater than 0 at each point on the open interval from a to b, then f increases on the closed interval from a to b. So if the derivative is always positive in this interval, then f increases on this closed interval. And if f prime's less than 0 at each point on the open interval from a to b, then f decreases on that closed interval from a to b. Okay? This is an important idea for us. Why? Because in the long run, it's going to lead us to, well, how can we find where the maximum value happens? We'll use derivatives to help us do that. Or where can we find, how can we find where the minimum value of a function occurs? So, where is the function f of x is equal to x cubed minus 4x increasing, and where is it decreasing? Okay, so what we'll do is we'll take the derivative f prime of x, which is 3x squared minus 4, and what we'll do is we'll look to see, well, on what intervals is that going to be positive, and on what intervals is this going to be negative? So to help me separate those, since this is just a polynomial, there's no place where it's not, it doesn't exist, I'll set that equal to 0. Adding 4 to both sides and dividing by 3, I've got 4/3 is equal to x squared. So x is equal to, and remember when you take the square root, you get two solutions, the positive solution and the negative solution. plus or minus 2 over the square root of 3. So that's where the derivative is equal to 0. And to help you, all of this does not count as justification if they ask you to justify something on the AP exam. A number line with those 2 points on them. So negative 2 over the square root of 3 and positive 2 over the square root of 3. Notice that partitions the number line into 3 different parts. Parts that are less than negative 2 over the square root of 3, parts that are between negative 2 over the square root of 3 and 2 over the square root of 3, and parts that are greater than 2 over the square root of 3. Okay? And what we can do is we can analyze the sign of the first derivative within each one of these. Now, for this particular problem, it's actually kind of easy because this is a quadratic, right? And it's a quadratic that has a positive x squared term, which means what about the shape of our parabola? It's pointing up. So if we were to draw f prime, I'm not going to actually draw all of it, but it would look something like this, right? So over here, f prime would be greater than 0. Between these 2 points, f prime would be less than 0. And here, f prime would be greater than 0. Now, let's say that this wasn't a nice quadratic. Let's say it was some other more complicated function, something that, say, had a natural log and sine and all those other kind of things.
Should have studied further.
Well, what you can do is to test it, you can just pick a point in each of these intervals, substitute it back into the derivative, not back into the original, because I'm interested in the sign of the derivative, and see, is the derivative positive in that interval?
This would be, it would be easy to use -1, 0, 1.
Well, -1, 0, and 1 are all in this interval.
Square root of 3 is like 1.
Isn't it? Let's see. So -2 over 1 point something, would that be more or less than 1? So if you had like 2 over, let's see, 1.5, that's going to be less than 1, right? So yeah, -1 and 1. But, if not, use 10.
Or you could do 2,000.
Sure. You can use anything in this because we know that these are the only what are called critical points where the derivative is 0. So we know that the function's not going to change sign anywhere else. So f is increasing on the interval from negative infinity, and that has to be open because it's not a number, to -2 over the square root of 3, and that's closed.
It looks like a bullet.
And on the interval from 2 over the square root of 3 to infinity, and f is decreasing on the closed interval from -2 over the square root of 3 to 2 over the square root of 3.
Why close interval? Reason?
Because it's on.
Because of what we said right here. If f prime is less than 0 on the open interval from a to b, then f decreases on the closed interval from a to b. Okay, and this is where people get into trouble because we're talking about increasing or decreasing on an interval. We almost never, and I hedge it a little bit by saying almost there, but we try to avoid it, talking about increasing or decreasing at a point. We always talk about increasing or decreasing on an interval. Okay? And that's where people get into trouble because they're like, well, wait a minute, you're saying that it's increasing at negative 2 over the square root of 3 and decreasing at negative 2 over the square root of 3. I'm like, no, I'm not. I'm saying on this interval it is increasing, or this interval it's decreasing, not at that particular point. Okay? Any questions? Okay. And that is it for today's lesson. I'll give you back your tests and we'll go over those.